research and nothing like that. So,
I looked up
just the design associated.
and then also it was.
Well, good morning. You notice we are going to be recording the lectures because we have a student overseas who's going to be watching those lectures. So what we'll do is post those on the web somewhere, and we'll send you a link so you can actually watch them later. But that's no excuse for not attending in person. Unless you live overseas. Last lecture we reviewed the scatter parameters very quickly, and the purpose was to get the lab experiments in sync. What's happening is we have two groups here in this room. The 5104G group, which is the graduate class, that's 3 credit hours, no lab. And then the undergrad class, which is the 4104, that's 4 credit hours, 3 for the lecture and 1 credit hour. So the lab is mandatory to the undergrads, the 4104 people. We can accommodate some visitors from the 5104 if you like to get to the lab and get your hands on things and actually lend support to the class. At some point, we may do some laboratory projects. You know, the 5104 people may elect. Usually, I make the project, something that you choose yourself. You submit a proposal, and we approve the proposal, and then you go on and do it. So the project could be computer simulation or literature search and report, and possibly it could be something like design and implementation. So we'll discuss that in due time, but like I said, if a limited number of you like to come to the lab, or maybe occasionally come and see if there's an exciting experiment that the 4104 is doing, like to watch, that kind of thing is encouraged. Right? Obviously, I don't want all 15 in there, or actually 16 grad students taking over the lab and denying the 12 4104 people from getting their hands on the equipment. Now, the lab options are going to be either Tuesday or Wednesday evenings from 6 to 9. So I'd like to see a show of hand for those who can prefer the Tuesday time. Right. How many of you prefer the Wednesday time? Do you have any objection to the Tuesday time? People that, because you are minority now. You cannot do Tuesday?
No.
All right, then Wednesday. People that said Tuesday, do you have an objection to Wednesday?
I don't know.
Yeah.
You have 11 on Wednesday? 6 to 9 as well? Same time?
Yeah.
How about earlier in the day?
Class.
Classes? Like we do, for example, 3 to 6.
Yeah. Classes are
On Tuesday?
On
No.
Wednesday.
On Wednesday. How about Tuesday? 3 to 6.
Class at
11.
5 to 8.
That's fine. You guys are not making difficult. Thursday night,
Oh, no.
you drop the class.
Dr. Riala, do you know what Doodle is? Have you ever heard of Doodle.com? It's a website where you can send out a schedule of the week
Yeah,
and have people respond.
right. The problem is if people can, people write their choices, but I can't get this interaction. It's going to take a week to do that. Several meetings. Yeah, I thank you.
Mhm.
But I think it will work better if we can just agree to a time right here. All right, how about 3 to 6 a.m.? Well, help me out. Okay. Monday is not possible because there's already a lab in the same room on Monday. So, if, what other options are there? So you guys have classes, tell me about the classes that you have, right? You have class on Tuesday from what time to what time? 5? 6:15.
5 to 8.
5 to 8. Okay, so Tuesday is gone. Now, Wednesday, what are the classes?
I have a lab from 6 to 9,
6 to 9. Anything else?
and then there's a class that ends at 3:20.
Okay, class at N 3:20. So 3 to 6 is possible. You know, I mean, 3:30 to 6, okay, whatever, yeah. So something in that range. So 3:30 to 6 o'clock on Wednesday is possible?
I can't do
You can't do it.
it. I have
He's
class
waiting
at
until
4,
the last minute to
4:05.
bomb our ideas.
Yeah.
Right. Thursday is similar to Tuesday?
I have that from 6 to 9, 7 to 10, sorry. So that from 7,
How about from 3 to 6 on Thursday?
cancel at 5.
Can we do something till 5?
How about the weekend? You know, I'm serious, you know, we've got to have a time. The thing is, usually that is scheduled ahead of time, and therefore when you sign up, you arrange for your schedule. But, you know, the way it's happening now. So, Sunday afternoon? Hmm? Okay, any problem with that? Now, Sunday afternoon, we can choose 2 to 5, you know, we don't have to go to evening. You guys all supposed to have access to the building, so you shouldn't have any issue coming and I'm waiting to hear or see the reaction on the GTA's face when I tell him something. All right, so we'll do Sunday afternoon. I hate this postpone. Okay, so now we have the lab schedule out of our way. We can get started with our class material. Now, any people unhappy about Sunday afternoon?
Yes.
Can you find another solution? Well, let's start with that, and if things work out, like, you know, people drop out from other class and all that, we can reschedule, right? So at least, and it's not gonna be this Sunday, obviously, the following Sunday, okay? So this week is out, and we may not even start the following Sunday, because we were supposed to be starting the week after that. But we'll see, I'll let you know. If things get in order and the lab is ready, we will have a session on Sunday.
Is it going to be every Sunday after that?
Hmm?
Is it going to be every Sunday after that?
Yeah, it's weekly lab, it's weekly. We have 10 experiments to do. So that's 10 weeks out of the 14. So that means it will be about 4 weeks that will take off. Either, we already took a couple of them at the beginning, so we'll have 2 other weeks that will maybe towards the end or something. We'll work things out. It's difficult to schedule things after everyone have settled their schedules and are happy about the way things go. But anyway, so we get, yes,
Is there no reason that half of us can do Tuesday and half of us Wednesday or something like that? Or,
it's unfair to the GTA to spend twice as much time. And usually they are assigned a certain number of hours to work every week, and they get their PhD work and lots of other things. So, we'll see. Maybe we can, you know, like I said, let's just leave it for that for now, and as a tentative, and hopefully, I don't like it either, believe me. Okay. I hate to do that to myself, and therefore I shouldn't like it for others.
Why don't you just put it early morning?
Hmm?
Why don't you just put it in early morning, like 7 to 10?
Early morning, like what?
7 to 10. something like that.
7 to 10 possible for anyone here?
What day?
Any day.
Tuesday.
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 7 to 10 Tuesdays?
Yeah, that works for me.
Yeah.
That would be great.
No.
No, it's not. Only one person is going to spoil it for us. You have the veto right. You can veto every decision we make. All right. Okay. At least I have a tentative schedule. I'm going to send a class call there to get your inputs, and I'm not going to do it until the schedule settles, which is going to be Monday. I think the ad drop ends today, so Monday I will be sending that, so you can tell me about your honest schedule, right? Not your desired schedule, and then I'll see if I can work something out. Even if we break it to 2 time slots, 2 hours here and 1 hour there or something, we'll see. It's best, obviously, to do a full 3 hours in the row to get the maximum benefit of the lab schedule. We can break it into 2 halves. Okay. Now, we are going to start with transmission lines. Okay? And you've had some back experience with those in the undergrad fields, I hope. Some of you may have more than others, but we have to go through to make sure that we are all on the same page, with the topic. And before I get into the transmission line analysis, I usually like to talk about transient and harmonic analysis, the difference between the two of them, and how does time domain relate to the frequency domain and all that. Because most of the work that you guys have done was with the harmonic analysis, the frequency domain, and the J. And I usually ask my class, and those of you who had me before, remember the question about what is J about, right? So, can anyone explain to me what J is? Imaginary quantity, right? Square root of -1.
90-degree phase shift.
90 degrees phase shift. Anything else? Okay. Well, you need to read this chapter. I already opened Scholar, and I uploaded this chapter in there, right? So you can read that chapter. It's only about, I don't know, I can't remember, a few pages. 14 pages only, right? And back at the end of this chapter here, the last 3 pages, there is an addendum. It explains the phasors and the concept of the complex numbers and all that. And at the end of this addendum, at the end of this chapter, where is it? Okay, here it goes. All right? It's called The Mystery of J and Imaginary Numbers, right? This is a good read that you can read in a short period. At the same time, you get some insight about this quantity. And the whole idea is, if I were to go back and talk about harmonic analysis, basically harmonic analysis is represented by projection of an angular motion of some form. If you imagine that you have a point here that rotates around a circle with constant radius and the varying angle here, and the angle here is a constant speed with time. The angular velocity is omega, right? The projection of that on this axis here is a waveform like this, right? That's what we call the harmonic motion. There are all sorts of other motions, there's linear ramping and clocks that go up and down and all sorts of other shapes. But this particular one here is important in the electrical engineering in particular world, simply because it determines one tone, one frequency. And we know that we have a spectrum of frequencies that is open for us to use in different applications. We send our signals in different frequency bands, and we try to limit our usage of the bands according to certain scheme. So if you have this kind of motion, if you have this kind of variation, if you have this kind of signal, that's a one frequency, a single frequency, right? And this particular representation here, which is called the waveform, right, or the harmonic wave, is basically contains all the information that we need about this signal here. It contains information about the amplitude and the phase, the point where it started. If you take this representation here and do projection in the other coordinate, you will see a similar thing, right? This one here is, complementary to that. It doesn't have any new information. There's no new information. Right? Whether you represent your signal this way or that way, either of them give you a full representation of your signal. So this representation typically goes as A cosine omega t plus phi. You can also write it as A sine omega t plus some other phase angle. And I should call this differently, by the way. Some of the things that I discovered that needs to be modified in this graph. All right. So usually we use this representation and go on with that. That's a typical thing. We like to always represent things in the cosine, and we work with this one. The thing about the J, all right, comes as a convenient tool to allow you to do the math in much simpler form. And it's all because of the Euler formula, which says that you can represent things with the phasor of A e to the j phi as two parts, A cosine plus J sine. Well, the cosine part has all the information. The sine part doesn't add any new information. Right? So in the addendum part, I argue, I say, well, suppose I have this picture in front of me. I have to get rid of this update thing. I hope it doesn't restart on me. I don't know. I say, suppose we have this representation, and I decide that I want to form a package between these two. I already have all the information in one package. Why do I need the other one? Just like I said, it's going to be like a mathematical convenience. Suppose if I want to decide to combine these two in a term or a package that I carry in my math for some reason. Obviously, if I add this to that, and expect to do process on the combination of the package, I don't want that to alter the nature of my signal or my results, right? So I argue, if I were to say A cosine omega t plus some packaging coefficient, let me go down to the addendum now, because that's where the discussion goes about this packaging term. Okay. Right, suppose now I decide the package term for the harmonic signal A as A cosine omega t plus some coefficient q times A sine omega t. And that q here is a linear coefficient that combines the two. And I'd like to make sure now that whatever I do to the PA does not introduce any errors to my main term, which is the cosine. In other words, the presence of q and the sine is not going to spoil it for me. So through that argument, I assume that there is another signal B, and I say if I combine the A and B, add them, multiply them, do all these kind of things, at the end, I should be able to get the same exact result that I have, or that I should get if I do only the cosine. So I check the scaling I check the addition, I check the multiplication, I check all these things, and then I discover at the end that I have to have this cube should be, or q squared should be 1 angle pi or minus 1. The only way that this will work out, the only combining coefficient, q has to be q squared equal to minus 1, or q is a j. So based on that, we see that the presence of this j is a mathematical convenience that enabled us to combine the whole picture, right? Without any additional information and without distorting the mathematical processes here. And therefore, we see the convenience of the usage of the Euler formula, which is right there at the end, which is basically the C as a phasor is expressed as C e to the j, some gamma, for example, that can be broken into C cosine gamma plus j sine gamma. This by itself is enough. That's why we want to get back now to the physical world. All what we need to do is take the real part of that. So after you finish all your process, you know that your real part is reserved to contain the proper answer, the correct answer with no errors. Introduction of the j term and the sine term is not going to spoil it for us. So if you want to get back to the time domain or the real world, without the imagining, you simply take the complex. So if you start with a real signal and you want to convert to the phasor domain, what you need to do is add j sine that, and now work with your phasor. After you finish all your processes, you take the real part, you come back to your real signal. Right? The real signal. So the conversion between the transient analysis and the harmonic analysis. We start with the transient analysis, and at some point we want to convert to the complex domain or the phasor domain. We add the j term. We finish the process, and then once we get the final result, we take the real part. Okay? So which domain do we use? So we have two choices here. Time, frequency. These are, we get that from the, I believe that's early in the chapter. The table is already there. Yeah, there's a table right here. I'll give an analogy here. I say, people in England speak English and people in France speak French, right? That's a conventional thing. If you have people in France that speak English or people in England that speak French, that's not conventional, but it's valid. At times, you have to use a different language to express something in particular. Similarly here, right? We have time domain, we have frequency domain. And we've got two possible states that we need to work with, either signals that are in transient state, or systems that are in transient state, or systems that are in steady state. It's conventional to express signals and systems in the transient state and the time domain. And signals and systems in steady state conventionally are expressed in the frequency domain. But occasionally we need to do the other. Occasionally, we need to do a steady state analysis and express it in the frequency domain, or we need to do a transient analysis and express it in the frequency domain. So, you know, the two languages are available to us, and we can use them as needed in the, and you will see, you know, sometimes we are working transient state and we'll do that, and we come to a point where we can't continue for some reason, and we find it more convenient to go there, although it's not conventional, and vice versa. So you all have seen the bounce diagram before. And typically, the bounce diagram is done in time domain because you can see the signal going, bouncing back, reflecting back and forth. We will do it in 3D. That's very unconventional. I'm doing a steady state analysis in the time domain, right? And I'm doing transient in the 3D. Now, when we study transmission lines, we use the physical modeling of the transmission line itself. We did not do a field analysis. And the reason for that was that it is much more convenient. But like I mentioned to you, I believe in the first lecture, that with that, we are doing an oversimplification and we're only seeing the dominant mode that happens in the transmission line. To see the higher order modes, we need to go to the field analysis. And the field analysis starts with Maxwell's equations. So we will do the same thing again here. We'll do the transmission line using the physical model, the RLCG model. And we'll see the wave equations, and we'll see the bounce diagrams, and we'll see all these things. And when we get to the waveguide, we will do the field analysis. The transmission lines in the field analysis actually is a step of complication beyond that of the waveguide. So the field analysis of the waveguide is easier than the field analysis of the transmission line. So the field analysis of the transmission line will come as a later step beyond that. Now, like I said, I'd like to recommend to you to read this chapter because you will find it very useful. All right? Chapter 2, which is the transmission lines, is also loaded in Scholar under resources. So if you want the resources, you will see one for the harmonic analysis and one for the transmission line. Now, any of us here in the class that have not seen transmission line analysis before at all? There's nothing wrong with what you say, and let me know now. Right? That will let me decide how fast I go.
I haven't done transient part of
You have?
Haven't done transient.
You haven't done transient part of it.
Yeah.
Yeah, that's typical, and I'll show you that part. I'll emphasize this part, that's for sure. I'm sure the other people in class have the same situation. All right, so this part here I reviewed with you on Monday, which is basically why we do transmission lines, why we do high frequency analysis differently, and on Scholar I fixed those numbers. I discovered that there was some digit error here in those numbers, so I fixed those. The one that you download will have those numbers probably. Okay, so what is it about the physical modeling? Well, we are using our tools of circuit theory. And we know that the tools that we have in circuit theory were actually derived based on the field theory. Right? In field theory, we've done Maxwell's equations, we've done the Gauss's law and Faraday's law, and all these things. Eventually, we came to the point where we defined the resistance, we defined the capacitance, we defined the inductance, and we have reduced Ampere's law and Faraday's law and all these things to KVL and KCL. So the laws that we're using in circuit theory are nothing but a simplification or a practical representation of the field theory findings in simple circuits. So it's just like going through another layer of approximation here, all right? So when I use the physical shape to derive some approximate circuit or equivalent circuit or a model for this, like, I give you this and tell you, go use this in the lab, so obviously you know the characteristics of that, you know the dimensions, so you can represent that as a piece of dielectric with this particular shape and have that much epsilon, and therefore if I apply some voltage here, that will be that much capacitance, you know. The physical shape eventually was converted to a circuit model, and I represent that circuit model in an equation, right? Same thing, if I give you a piece of X or a microstrip or any of these shapes, eventually we can come up with a physical model that represent that shape. So the conductors that I have will have some internal resistance. The presence of these conductors form magnetic behavior, and therefore I've got some inductance. The dielectric between the two conductors have some leakage currents in them, right? Because dielectric is not perfect, and therefore there is some what we call conductance or leakage resistance, and also there's some isolation between two equipotential surfaces, and therefore there is some capacitance here. And hence the model that we come up with, that I've got resistive behavior, inductive behavior, conductance, capacitance. All these are derived in an approximation to the field solution itself. So it's getting around the complexity of doing the analysis using Maxwell's equations. So based on that, I can see now that my transmission line, which is right there, has this internal resistance everywhere, internal inductance everywhere, conductance, capacitance, all these are happening everywhere in a distributed fashion. Now, if I was working at low frequencies, I could have said the total resistance is, total inductance is, total capacitance is, total conductance is, and that would be my model for the transmission line between the ends. But I know very well that this length here is not insignificant compared to the wavelength, right? Because I'm going to be working at high frequency. At low frequency, you can do that, right? At low frequency, we said that the size of the circuit is much too small compared to the wavelength. If this is centimeters and your wavelength is kilometers, you can do that. But if this is centimeters and your wavelength is millimeters, obviously you cannot do that. So you have to now work a distributed circuit analysis for this frequency range. So what we do is we take an increment, hopefully small enough, delta z, and we look at the model for that. That delta z here is much, much too small compared to the wavelength. And in the limit, I'm going to take it to 0 anyway, so I will be covering a wider frequency range with that. The limitation in this analysis, like I said, in coming up with those numbers for the particular frequency range. Right? Converting the field solution into the RLCG model is the limitation here. So I end up with a delta R, a delta L, a delta C, and a delta G. And that's my model for an increment here. You notice I'm using the notation of R sub Z, and L sub Z, and C sub Z, and G sub Z, and that's indication that these are not the regular resistance, capacitance, inductance, because these are actually per unit length. These parameters, the R sub Z is per unit length, so the resistance of this element here is the per unit length times the length. So the length is delta Z, so R sub Z times delta Z gives you the delta R here. That's your delta L, that's your delta G, and that's your delta C. At the same time, I label my currents and voltages. I say at this location here on the line, I call this I sub Z and V sub Z. Right? And therefore, after an increment, it will be I sub Z plus delta Z, and V of Z plus delta Z. Right? And I write my equations for this increment, and take the limit as delta equals to 0, I end up with a differential equation. This line here supposedly is sitting between a transmitting end or a source end and a load end. For our analysis, we'll just confine ourselves here and we'll worry about those later. those eventually will become part of the boundary conditions for this region. So I'm doing my solution for this region here, and these will determine the boundary conditions of my solution. So I look at this part here, and we start writing the equations. And to write the equations again, we have two choices. Either we do a time domain language or frequency domain language. And let's see here, I probably need to expand this a bit more. Let's go to, let's see if I can do 150. And still display the whole thing. Okay, here we go. So for the time domain, the notation is the lowercase notation. All right? And for the frequency domain, I'm using the phasor notation, which is the uppercase notation. Now, Z here, I'd like to change it to a script Z in my next graph, so it will not get confused with impedance, although impedance will be the uppercase Z. This is lowercase z, but if I use a script one, it will be easier on the eye. At some point, you'll see the impedance, and that will be coming later on. And the impedance is defined only in the frequency domain. There's no definition for impedance on the time domain, as we report. So we write our equation for the voltage is Z plus delta Z at this end. From the KVL around the loop, the voltage here is equal to voltage here plus the voltage drop across the segment in between, and that's the R times the current plus LdI by dt. So that's your increment in between here. So this is V of Z plus delta Z, and this is I of Z, and this is V of Z. So V of Z plus delta Z and T is equal to the voltage here, which is V of Z, plus the drop here, which is going to be I of Z and T, should be NT all time, okay? Times delta R plus L di dt plus delta L partial